Welcome to the second video about oxidation of alcohols, called Oxidation of Alcohols Part 2. In Part 1, we learnt about how primary alcohols could be oxidised into two new types of compounds, aldehydes and carboxylic acids. We went on to look at how secondary alcohols could be oxidised into a new type of compound called ketones. And we also looked at why tertiary alcohols could not be oxidised. Remember, the oxidising agent was something called acidified potassium dichromate solution. And you needed to heat up the primary and the secondary alcohols with this solution in order to carry out the oxidation. Whereas secondary alcohols could only turn into ketones, primary alcohols could turn into aldehydes or carboxylic acids. And to control which one of those two things was made, you needed to change the reaction conditions. And in the first video, we introduced the words distillation and reflux. And the point of this video today is to look at what those two words mean and the kinds of equipment that might be used to carry out those two processes. Now, we have a bit of a fundamental problem here. I don't actually have any of that equipment with me to be able to do these videos. However, I have improvised. When you start to do practical organic chemistry, you learn to use certain types of glassware called Quickfit. And the first piece of Quickfit equipment that I want to introduce you to is something called a pear-shaped flask. There's the pear. So we're looking for a flask which is something like that shape. Now, here's a paper cutout of what it would look like if it was two-dimensional. There is some similarity. Now, the pear-shaped flask is used to heat up the primary alcohol with the acidified potassium dichromate solution. So let's imagine we've got some of that stuff in there. Let's imagine we're going to heat it up. Now, there's a fundamental problem here. If you heat up organic chemicals, like primary alcohols, and those organic primary alcohols are oxidised to form aldehydes, the primary alcohols and the aldehydes are going to be very volatile. Remember, volatile is to do with how easy it is for something to turn into a gas. So if they are very volatile, they have low boiling points and turn into a gas easily. That means we're going to have vapours coming out of the top of the pear-shaped flask. And those vapours are going to be very flammable. And if we've got a heat source, like a Bunsen burner, there is the potential for fire. Now, I know that sounds very exciting, but it also sounds very dangerous. So we need to develop the way that we heat our primary alcohols to stop the fire business happening. Now, the great thing about Quickfit is there are lots of pieces and they all fit together. Wouldn't it be good if we could actually stop the vapours just spilling out at the top of the pear-shaped flask? Wouldn't it be good if we could actually condense those vapours and turn them back into the liquid aldehyde? Well, here we've got a setup which enables us to do this. Pear-shaped flask is where the heating occurs. The vapours pass up through this tube. They would go straight out the top, unless we put a bung in here. We'll talk about that in a moment. And if that's the case, the vapours have to pass through this piece of equipment, a condenser. Now, the condenser is made up of two tubes. We've got the central tube, which the vapours pass through, and an outside tube, which encapsulates that inner tube. And in the outside tube, we put cold water. Now the cold water clearly makes the condenser cold, and the vapours which are passing through the inner tube will become cold and will condense and turn back into a liquid. The water which comes out of the other side of the condenser is going to be slightly warmer. Now what we don't want are the vapours or the liquid aldehyde just dripping out of the end here. Otherwise, you guessed it, fire. So what we can do is we can capture that liquid, that aldehyde, in an alternative flask. This effectively is a way of heating up safely a primary alcohol with the oxidizing agent. The vapours can be condensed back into a liquid, in this case an aldehyde, and that can all be done safely away from the heat source. Now, rather than using a Bunsen burner, what we should probably do is use an electric heater, sometimes called an electric heating mantle, or a hot sand bath, or a water bath. And then there are no flames nearby. This is called distillation. And if we do a distillation with a primary alcohol and acidified potassium dichromate solution, what we will make will be an aldehyde. Now, just going back to what's going on over here. If we were to put a thermometer into this part, a thermometer pocket at the top, which stops the vapours coming out there, and a thermometer opposite the top opening of the condenser, the reading on the thermometer will tell us the temperature of the vapours which are at this point of the equipment. And so if we've got something condensing in the condenser, it effectively tells us the boiling point of the liquid which is being produced at that point. Quite handy. Okay, so that's distillation. What's reflux? Now, I'm sure some of you may have used the word reflux before, and sometimes it's used when you've had something to eat and you get that kind of acidic feeling coming up your esophagus. That sometimes is called reflux. Now, reflux, pear-shaped flask, we've now got our primary alcohol and our acidified potassium dichromate solution. This time, we don't really want the vapours to escape at all. We want them to stay in that pear-shaped flask. Now, what we can't do is just put a bung on there, because heating things up in a sealed system isn't a particularly safe thing to do. So what we do, we just put the condenser on the top, but vertical. What happens now is we heat up the pear-shaped flask. The primary alcohol is oxidised. As it's oxidised, an aldehyde's formed, and the aldehyde will, because of its low boiling point, move up into the condenser. Because the condenser is cold, the aldehyde will recondense and go back into the pear-shaped flask. Any of the primary alcohol that evaporates will also condense and go back into the pear-shaped flask. Because we've got, if you remember, some cold water going in at the bottom of the condenser and slightly warmer water coming out at the top. So reflux is a way of continually heating a reactant, and any vapours are returned back into the reaction vessel. I think that was an exam question at OCR around about 2006. What is meant by the term reflux? It was a 2-mark question, as I remember. The answers were continual heating with vapours being returned back into the reaction vessel. Now, the benefit of this system is it allows our reactant, the primary alcohol, to undergo complete oxidation and be turned into a carboxylic acid. That's because the aldehyde can't escape out of the system, and the aldehyde is being returned back into the reaction vessel, the primary alcohol is being returned back into the reaction vessel, and ultimately the reflux enables that primary alcohol to be turned into the carboxylic acid. Now, if we were going to try and oxidize a secondary alcohol, if you remember, the secondary alcohol can only turn into a ketone. We'd probably use this setup as well for the secondary alcohol, because it would mean that the secondary alcohol would be turned entirely into the ketone. Tertiary alcohols cannot be easily oxidized. They can't be oxidized by acidified potassium dichromate solution. We talked about that in yesterday's video. That's the end of oxidation of alcohols, part 2.